We have 1,450 employees, civilian employees. We have 3 military, including me. And so the Corps of Engineers is military-led, but civilian-run. So on Engineer Week, we have a great lineup for you this week. You know, the least of which is me. I'm the opening act here to get us started. But we have the video for you after this, USACE mission video. We've got a virtual tour of Lookout Point Dam, one of our dams out in the Willamette Valley, to talk about structural and mechanical engineering, and then automated controls and cybersecurity. We'll talk about multidisciplinary engineering. Throughout the week, we'll talk about hydraulic engineering, civil and construction engineering, electrical engineering, engineer in training, our EIT program, and then how to be successful in a STEM career, how to get started, college preparation, and what you need to do. And not everyone needs to go to college, right? We have tradespeople that have very important roles here in the Portland district at our operating projects. And so lots of opportunity to join the Corps of Engineers, a STEM-related career, a career of service. We serve with great purpose here, and I'll get into that here in a little bit with the mission sets that we have. We're really proud of what we're able to do and the way that we're able to serve the people of the Pacific Northwest. And so that's my opening. Do we have the slides up? I don't see anything.
Oh, yeah, I'll bring them up right now.
And I see in the chat about 24 students in an intro to engineering class. Teacher is Col Jay Wiley, U.S. Marine Corps. All right, Colonel Wiley, thank you. Thank you for your service, and thank you for what you're doing for these young adults and teaching them the right way, I'm sure, and a lot of life lessons, a lot of leadership there. That's awesome. My dad was a high school football coach, and you know, when I retire at some point, I've got 23 years active duty right now. When I retire at some point, I want to make sure I'm able to make a difference, and I'm thinking about potentially going back and teaching high school, coaching high school football, like my dad did, and that's outstanding. Thanks, Colonel Wiley, for what you're doing. Okay, so the U.S. Army Corps of Engineers, we've been serving the nation since 1775. The Army's birthday is June 14th, 1775. The Engineer Regiment's birthday is June 16th, 1775. And so George Washington and the Continental Congress knew very quickly that we needed an Engineer Regiment to win the Revolutionary War. One of the oldest engineering firms in the world, if not the oldest. We serve the public and the military. I've been a combat engineer. I've been a bridging engineer on the green suit side. I've been a construction engineer on the green suit side, and I've been with the Corps of Engineers. And so the breadth of missions that I've gotten to participate in, it's never gotten old. You know, much different than being an infantryman or, you know, a tanker as far as the Army goes. You're an infantryman and a tanker, you know, throughout your career. And there's some great leadership there, and we need those guys. I love being an engineer because I've gotten to do so many different kinds of things in service to my country. Let's see, we engineer solutions to the nation's toughest challenges. And so Colonel Wiley can remind you for the high school kids, high school students, if you don't remember, but the alternate care facilities that the U.S. Army Corps of Engineers built for COVID. General Semonite, Lieutenant General Semonite, the Chief of Engineers, was on the national media quite a bit, hitting home runs and speaking confidently about how the Corps of Engineers was going to deliver these alternate care facilities to make sure that we didn't run out of bed space early on in the pandemic. And he was able to speak so confidently because he knew that he had a world-class workforce behind him that was committed, regardless of the circumstances, regardless of the environment, committed to serving the people of this great nation. And that's what we have here in the Portland District. That's what we have here across the Corps of Engineers. Okay, so let's go ahead and go to the next slide. Okay, a little bit about me. I've got, like I said, 23 years of service. Right now, almost 24. And here's me by the numbers. There's a picture of my family, a little bit more about them in a second. We've moved 11 times. I've got 3 combat deployments. We've had 4 dogs over the years, 2 cats that didn't last very long in my house. Sorry for you cat lovers out there. 2 kids, 2 great kids, 1 wife. That's the number that I'm most proud of, that number 1 wife that has stuck with me through 23 years of service and all the moves and deployments. And so the reason I wanted to mention that is, you know, when you make a commitment to someone, keep that commitment. Make sure that lifelong commitment, that's the one you want to make. You found the one, and that's the one you're going to stick it out with through thick and thin. We've had our ups, we've had our downs, and she stuck with me somehow, by the grace of God. All right, couple keys to success. Work ethic. You know, why am I sitting here as a colonel in the U.S. Army? You know, when I was a brand new second lieutenant, graduated from West Point in 1998, and, you know, there was God, and then there was my battalion commander, right? And I thought, there's no way I'm going to make lieutenant colonel. There's no way I can do that, right? It was just so far away. Well, through work ethic, servant leadership, right? Your people aren't there to take care of you. You're there to take care of your people. Servant leadership, great team player. Be a great team player. Have a positive attitude, and you can't lose, right? And I've always told my young officers, you know, when the Army says, and one of these days, the Army's going to tell Helton, hey, Helton, God bless you, we don't need you anymore, right? And that's okay. It's going to happen to every single service member. And so if I carried myself in that way, if I had a great work ethic, if I was a servant leader, as a great team player, had a positive attitude every day, my boss, my colonel, my general officer, whoever it is going to be the first one to pick up the phone to an employer and say, hey, Helton's the guy you want. And so those are my keys to success. So my family, Michelle, we live up in Vancouver. My wife found a place. We moved from DC. I was in the Pentagon before this assignment. We moved in 2020. My wife found a place that up in Vancouver that was being constructed, so it was brand new construction. She got to design everything, so she's really happy. Every little girl's dream to design her own home, and so she got to do that, pick out countertops and paint and everything else, cabinets. My oldest son goes to Clark College. He ended up going to 3 different high schools, and so with military service, there's sacrifice, and it's not just the service member that sacrifices. It's the families as well. My son ended up going to 3 different high schools. Not easy to do, but the resilience that he gained from it, I'm really in awe of how he's handled it. He's going to Clark College right now, making great grades. He'll get his core classes done, and he wants to go into music production at some point here in the near future. We've got to find the right college for him. And then my youngest son, Seth, oldest son's Jake, youngest son Seth is 11, 6th grader, plays violin. He's passionate about the violin. I love it. He comes home and plays me a new song after every practice, and the smile on his face after I tell him he's going to go pro someday is just priceless. And so that's my family. Oh, and we have a dog. If you get to go see the movie Dog, I took the boys to see Dog last night. Great movie about a military working dog, Belgian Malinois. We recently got a Belgian Malinois. My wife is in need of a service dog, and so they're really intelligent dogs and well into his training at this point and doing great. I mentioned fun. We have a lot of fun in the Portland District. My great public affairs office has fun at my expense. sometimes, and you've got to have the humility as the boss to allow your folks to have fun at your expense. Hey, sir, what are you up to? I'm chilling with Herman. So Herman, the sturgeon, is at Bonneville. If you get to go out to Bonneville, go out to the hatchery area, you'll get to visit Herman like I did, maybe take a selfie. And anyway, so that's that. Let's see, talked about family, career. So I talked about career a little bit, 2 stints. This is my second stint with the Army Corps of Engineers. I was with the Baltimore District back in 2008 to 2011. I actually loved it so much, I thought about getting out of the Army and early and seeking a career with the Corps of Engineers as a civilian. Just a great organization, like I said, that gets to make a difference for the people of this nation. Really proud of the Portland District. Everywhere I go, and we'll talk about the breadth of the mission sets that we have, but everywhere I go, I'm floored by the professionalism, by the expertise that our folks have, by the passion for service and making a difference for the local communities, for the people of the Pacific Northwest, for the people of the nation. Just can't tell you how proud I am of this organization. Find a career that you're passionate about. So advice from Colonel Helton. Find a career that you're passionate about. Find something where every day you get to wake up and you say, I get to do X, Y, and Z, as opposed to I have to do this, that, or the other. That's a big difference, right? I've got a job where I get to get up and talk to a group of high school students. What an honor, right? I get to go out to an operating project. I get to go out and visit one of our dredges and gain an understanding of everything that's going on so that I can make a difference in an up and out way. If they need a resource or something like that, I can make a difference for the people that are getting the job done. And so I get to as opposed to I have to. With a STEM-related career, it's really a great way to make a difference for others. And so you rode a bus or you drove to school this morning, right? That road was built with the expertise of an engineer, of a mathematician. You cross a bridge, you need those engineers. You need those STEM-related smart people, civil engineers, mechanical, structural, to build the building that you're sitting in right now, so you can stay out of the cold and listen to an old colonel talk. And so STEM-related folks, in a STEM-related career, you get to make a difference. In the Corps of Engineers, you get to make a difference in a really direct way, as we'll talk about here in a minute. Okay, so let's go ahead and go to the next slide. Okay, I'm on Find Your Superpower in a STEM Career. What's your superpower? And again, what I was going to say here is what I've already said, right? I'm amazed at the expertise of our and passion of our engineers, of our scientists, our fish biologists. We just have phenomenal people, and that really, it seems like to me anyway that they've got a superpower. So what's your superpower? What do you want to do to make a difference for people? Okay, engineer your future. Here's a list of various occupations within the U.S. Army Corps of Engineers. And I was surprised by this when I first came on to the Corps after, serving as a combat engineer and a bridging engineer, construction engineer for a little while. Really, really amazing the variety of occupations that we have and expertise that we have. 32,000, actually it's more like 35,000 civilians now across the U.S. Army Corps of Engineers, 700 military personnel, so we're way outnumbered. The civilians have us, again, military-led, civilian-run. Okay, next slide. Okay, just quickly, here's the makeup of the Army Corps of Engineers. We have 9 divisions. The Northwestern Division is the division that the Portland district is in. The division headquarters is also in Portland, not in the same building, so I get to be a little bit away from the flagpole there across the river. I've got a great view of the Willamette River, by the way, from my office. Anyway, we've got the Seattle district, Walla Walla district, Omaha, and Kansas City district, all within the Northwestern Division. And the three Western districts, Seattle, Walla Walla, and Portland, work together extremely well across our business lines, across our mission areas. We serve overseas, the Transatlantic Division. You know, we're not in Iraq and Afghanistan in great numbers anymore, but when we were building facilities in support of the overall mission in Iraq and Afghanistan, and then we support other allies and partners in the Middle East, Europe, and other locations. Okay, next slide. Okay, this is the Portland district. Little overview. We have 97, almost 97,000 square miles of land and shoreline in Oregon and southwestern Washington. We balance the region's competing needs for navigation. Flood risk management is huge. Hydropower production. We produce about 20% of the hydropower in the Pacific Northwest, or not hydropower, 20% of the power through our hydropower production in the Pacific Northwest. Fish and wildlife habitat, disaster recovery, and then irrigation and recreation. We've got multi-purpose projects throughout the Willamette Basin. We have a few down in the Rogue River Basin down in southern Oregon. Then we have the first three dams on the Columbia River, Bonneville Dam, the Dalles, and John Day Dam, where we have, they're all locks and dams, so they have navigation locks. And if you've seen videos of the Panama Canal, it's kind of like that, right? It's the same idea, getting barges and ships up and down the Columbia River to ensure reliable commerce. We ensure about $24 billion worth of commerce up and down the Columbia River every year. It's pretty phenomenal. We have 18 channels and harbors that we dredge along the Oregon coast. We also dredge for our various channels and harbors in California. We dredge for the LA district, San Francisco district, Alaska district, and then we do underwater survey work for Hawaii district. Just got to go out to Hawaii and visit our dredge that is in dry dock right now, having some maintenance done on it. Okay, so that's it on that slide. Okay, our business lines. Talked about this briefly, but navigation. We dredge the Columbia River, so we have a federal channel in the Columbia River. We have two dredge vessels, one about 350 feet, the other about 250 feet, and we'll get to a picture of the dredge vessel, a dredge vessel in a minute. But we dredge, deepen the federal channel in the Columbia River to enable navigation, and we do the same up and down the Oregon coast with the channels and harbors. Water and flood risk management, life safety is huge for us. So our operating projects in the Rogue and Willamette Valley, the primary purpose is flood risk management and making sure that we do everything that we can to reduce the impact of floods and to ensure as best we can life safety of the people downstream. That's huge. We take that piece very seriously. Talked about the hydropower, and we'll go through each of these one by one in our slides, I think. So let's go on to the next slide. Okay, engineering infrastructure. So the Corps of Engineers help build, of course, the nation's roads, bridges, canals, levees, dams, and even famous buildings like the Capitol building. The Washington Monument was built by the U.S. Army Corps of Engineers. I've got a big book called Capitol Engineers that talks about all the infrastructure and all the buildings that the Corps of Engineers built in Washington, D.C. You see there a picture of, I believe that's the South Jetty at the mouth of the Columbia River. So we have a system of jetties that enable navigation as well. We have jetties up and down the Oregon coast, and then we have the big one at the mouth of the Columbia River. You know, that used to be called the graveyard of the Pacific. It was so treacherous. There were hundreds of shipwrecks over the years. And we built this system of levees to maintain that federal channel, to channel the federal channel where we wanted it to be, and to help the ships come in and out of the Columbia River to ensure that navigation. Okay, next slide. All right, navigation. So this is one of our navigation locks. And I got to do a basket ride, a lot of fun. Hop in a basket attached to a crane and go down and inspect our navigation lock, the lock gates and valves and the structural stability and everything else. And so this is an example of a navigation lock. Fills up with water. We have valves that bring water in and out to raise ships up or lower ships down in order to either come upstream or downstream. And so we have 3 of these within the Portland district, and then there's another one, McNary Dam, that the Walla Walla district has a little bit further up the Columbia River. Okay, next slide. Okay, flood control and water management. So we manage 21 dams that help reduce flood risk to the people of the Pacific Northwest here. We maintain 365 miles of levees and bank protection. And we completed 255 flood reduction projects, flood walls, levees, and channel improvements. And so the purpose is to save lives and reduce property damage by reducing flood risk with both structural and non-structural measures. Then on the water management side, you know, our dams and storage reservoir projects, and so the reservoirs behind our dams, we have 11 in the Willamette River Basin and 2 in the Rogue River Basin, and then, of course, the 3 that we have on the Columbia River. And so really the overall purpose, again, for the water management is to manage flood risk and provide water for hydropower generation, so huge hydropower generation capacity with our Columbia River projects. We do have hydropower production in our Willamette Valley projects, 9 of our Willamette Valley projects, but not as significant of production as our Columbia River projects. Really, really phenomenal. And what our team does and the engineering behind the turbines that we've built and we've had installed, fish-friendly turbines to allow juvenile salmon to safely go through our turbines is really amazing. And really back to the commitment, the expertise and commitment to producing hydropower while protecting the environment, saving as many salmon as we possibly can in the process. Nobody in the world does it better than the U.S. Army Corps of Engineers, and really, really proud of that. Okay, so talked about hydropower just a little bit. I know we're running short on time. Environmental stewardship. So I did want to mention this. I never would have thought before I came to the Portland district that the Corps of Engineers would be involved in saving species from becoming extinct. So the Fender's blue butterfly and the Kincaid's lupine, I think is how you say it. The Kincaid's lupine, if you've ever seen a Texas bluebonnet, it looks kind of like that, a little bit different color, more purplish. The Fender's blue butterfly feeds off of the Kincaid's lupine, and so you really need to save the lupine to save the butterfly, and we've done both. We've increased the numbers dramatically on Corps of Engineer lands, something our team is really proud of. We have environmental stewards, professional horticulturalists, biologists that are just passionate about saving the environment, saving various species out there. And so overall purpose is to restore ecosystem structure and processes and manage our land and resources in a sustainable way while leaving the smallest footprint possible. Okay, on to the next slide. You know, many people think that the Forest Service is the only organization with park rangers. The Corps of Engineers has a huge recreation mission associated with our operating projects and the pools or the reservoirs we have behind our multi-purpose dams. We have parks, and those parks require park rangers. And if you ever get a chance to visit some of our parks along the Columbia River or in the Willamette Valley or Rogue River Basin, some really beautiful areas. And we've got 135 recreation sites, 495 campsites, 3 visitor centers across the Columbia River with Bonneville, the Dalles, Lost Creek Lake, 55 boat ramps, and we support about 10.2 million visitors per year in a normal year. And so we really do take pride in providing quality outdoor public recreation, and that's another way that we get to serve. Okay, next slide. All right, emergency operations. And so I was really proud of the Portland District's response to the wildfires last, I guess it was September 2020. We built 129, I think was the total number, mobile housing units for Oregonians displaced by the wildfires. We worked hand in hand with FEMA to do it. Of course, we received once the disaster is declared, we received the money, the funding from FEMA to build these mobile housing units. And we took a lot of pride in doing it with speed and with excellence. We got the first 23 families in housing before Christmas of that year, and we started in November. And so to operate so quickly and efficiently, it took great teamwork. I talked about being a great team player. That's what it took. It took being a great team player with FEMA, with Oregon Emergency Management, other organizations out there to, again, make a difference for the people that we're serving. And we took a lot of pride in that. We also performed debris monitoring for the state of Oregon. So the state of Oregon, ODOT, Department of Transportation, hired a contractor to remove debris from burned homes, burned areas, businesses as well. And we monitored that. We had the expertise to be able to make sure that everything was being done appropriately. And we gave daily feedback to the state of Oregon, and their mission was more successful because of our efforts. And so we're really proud of that. We also, you see sandbags there for the mitigation of flood damage. The Portland District has deployed 82 folks, or we've had 82 deployments, sorry, more than 82 folks, 82 deployments for disaster response since 2011, 308 overseas contingency deployments since 2003. And so flood response, technical assistance, and I talked to you about the wildfires, but again, it's whatever we can do as engineering experts to be able to make a difference for the people of the Pacific Northwest or the people of the nation. If we're deployed down to, you know, a hurricane damaged area, that's what we're going to do. And so we take a lot of pride in that piece. So that's emergency operations. Next slide. Okay, this is what I was looking forward to. I've had the most fun boarding our vessels. We have 2 dredge vessels, the Essayons, that's engineer or French word for let us try. That's actually the Corps of Engineer motto. And, you know, in today's language, that was back in 1775 language, right? Let us try. It's not, you know, let me give it a shot. Let me try. No, it's, in today's terms, it would be more like, we got this, right? And so the essay-ons, I believe that's the essay-ons right there. We've got a couple of drag arms, one on each side, that acts like a giant vacuum that sucks up sediment from channels, the bottom of channels and harbors to make sure they're at the correct depth for navigation. And again, we take a lot of pride in that. It's really cool to own 2 dredge vessels. We also have 6 survey vessels. We go do bathymetry. We go survey the bottom of the federal channels that we maintain through the Columbia River channels and harbors. And also, like I said before, we do work for other districts and other areas, other states as well. But great mission, really vital to, again, the commerce that we enable throughout the Pacific Northwest. Okay, I think that's it. Next slide. And everything in between, yeah. Okay, become a team member. So, you know, it is, we can go ahead and go to the last slide. Become a team member, right? So U.S. Army Engineers for Engineering. So that's a really old poster, right? And you see soldiers and you see civilians. And the U.S. Army Corps of Engineers, the U.S. Army Engineer Regiment. You know, if you want to go Army, I would encourage you to do that. There's some great Marine engineers that I know. So shout out to Col Jay Wiley. I don't know if you're an engineer or not. I know every Marine's a rifleman, but I've known some great Marine engineers. The Navy Seabees, some great construction engineers. The Air Force has a civil engineering crew that I've worked with before. And so there are ways to serve in engineering in a STEM-related field in uniform, and there are ways to serve out of uniform. My bottom line is it's honorable to serve, whether you're serving in uniform or out of uniform. And, you know, I've gotten, I see it. Yes, Combat Engineer, 93 to 2018. Outstanding. I've got to connect with you, sir. Look, I'm looking forward to meeting you. That's outstanding. And so let me pass one more thing on to you. So I was a basic training and advanced individual training for engineers, battalion commander. And I would have young soldiers come to me wanting to quit. Because, you know, basic training's hard, right? And Colonel McKay can tell you, basic training's hard. It's not an easy thing, but it's absolutely doable, and nothing's personal. Drill sergeants yelling at you, that's what they have to do, and they break you down and build you up, right? And make you a better soldier, and really make you, I've seen people, young adults, transformed into young men and women in the span of 14, 15 weeks. It's really phenomenal. But I'd have young soldiers come to me and say, hey, sir, I want to quit. Well, okay, well, what do you want to do? Well, I want to go back home and go to school. All right, so how are you going to pay for it? Well, I guess I'm going to get a job. All right, well, let's think about this for a second. So you're going to go to school, you're going to get a job to pay for it. Got it. Okay, so when do you think you're going to go to school? What hours of the day? What do you think, about 8, 9 to 4 or 5 in the afternoon? Yeah, that's about right, sir. Okay. When are you going to go to work? 5 to 10, something like that. Yeah, that makes sense. All right, so when are you going to study? Well, I guess I'll study from 10 to midnight. All right, well, you know, millions of Americans have done that, right? But you're going to have to work hard. You're going to have to work your rear end off to be successful, right? And so I would tell them that, hey, you're already on the greatest team in the world, right? The U.S. military, the U.S. Army. Yeah, you're going to have your education paid for if you persevere through this. Become a soldier. Get your education paid for. You're going to have to work your rear end off. right, while in uniform. But, you know, there's no easy path to success. There's no, you know, I guess, lazy path to success, right? You're going to have to work hard to be successful in life. And so I'll never forget this one young soldier, after I gave him this talk, he says, "Sir, I'm so sorry for wasting your time. I'm going to stay." And so, and he stayed and he graduated, and I'm sure he's doing great things out there. But that's what I'll end with. You know, it takes effort. It takes it takes work ethic. It takes a positive attitude. Be a great team player, and you won't fail. You will be successful in whatever you choose to do. And again, find something where you get to say, every day I wake up and I get to do X, Y, and Z. And being a servant leader certainly helps in that. And just having that mindset that, hey, I get up, I get to go serve others, right? I get to go make a difference in somebody else's life. I get to go make someone else's work life better. It's made all the difference for me. Absolutely love what I do. Wouldn't trade it, and I would do it all over again, deployments and everything else included. And so that's my message to you. I hope y'all have a great week. We're all excited. The whole team's excited to be talking to y'all, and I am from Texas, by the way, if I didn't mention that before. Every once in a while, I won't just say y'all, I'll say all y'all, and I won't even realize it, and the team will point that out to me. But anyway, I hope y'all have a wonderful week and get something out of this, because I know the team's put a lot of effort into this. Ask tough questions. I don't see any questions in there, so I'm assuming you're saving all your hardball questions for our really, really smart engineers that are coming up soon. So I'll end there, and I know I went a little bit over, but it's a pleasure to talk to you. Please reach out to me, and Colonel McKay, I would love to get your contact information and chat with you. Thank y'all. God bless.
Thank you, sir. And McKay, I can unmute you since it's just you guys. Sir, do you have a couple minutes if they do have any questions?
Oh, I do. I just realized I said Colonel McKay. It's Colonel Wiley. Sorry, McKay High School.
Yeah. Well, in that case, if you guys have any questions, I can pass them on. How about I go ahead and get Brian and Bridget unmuted. Okay. And they have a very exciting presentation for today. Sir, thank you so much for joining this. That was a really encouraging speech. I enjoyed it.
Yeah, my pleasure. I wish I could meet you all in person, maybe sometime in the future, maybe next year, for those who don't graduate this year. But all the best to you, and take care. Thank you.
Thank you, sir. Okay, guys. So, Bridget, I have you set up so that you can share your screen if need be. Are you
okay?
Good to go?
Yeah, sure. Is my mic working?
No, stop sharing.
Yes, we can hear you.
Okay, thank you.
Okay, so this is Brian and Bridget Bell, and they put together a really cool virtual 3D tour for each of the dam sites. The cool thing is they did this, I think, during the time period where COVID was first occurring. And so that was very helpful for us because our access at the time to the sites was very limited. So it's Brian, I'll actually have you guys introduce yourselves because I know you are both in new, exciting positions.
All right. Thanks, Michelle. Yeah, we're having a little bit of technical difficulties today, so we're sharing a cube to give the presentation because Brian's computer doesn't seem to be wanting to work today. But you adapt. So my name is Bridget Bell. I graduated from Tulane University in 2007. Tulane's located in New Orleans, Louisiana. And I started my career in the oil and gas sector as a civil engineer with a structural focus. My husband, who will introduce himself in just a minute, and I moved up to the Portland area in 2014, and I joined the Corps about 2.5 years ago as a technical lead. And I was recently selected as Chief of Technical and Contract Section in the Willamette Valley. So I started that position last week. I'm still kind of drinking from the fire hose, learning all the new things I need to learn. Lookout Point is one of the facilities that my team and I help support, and it's what I'm here to show you today. But first, Brian will give a quick introduction of himself and the virtual tour system that we use.
All right, thanks, Bridget. Everybody can hear me okay? Awesome. So my name is Brian Bell. I'm glad to be here with you today. Thanks for joining us for E-Week. Glad to kick it off with you. I come, as Bridget mentioned, by way of New Orleans, Louisiana, where I was born and raised, actually. Went to Tulane University as well for my engineering degree. Although I will admit I spent most of my time in college on the stage by way of musical theater. So kind of an oddball in the engineering regimen and in the theater regimen. After graduating, I started working for the Corps of Engineers in New Orleans district. And shortly, a couple of years after that, moved up to Portland to take a job in the Hydroelectric Design Center. So I worked as a mechanical engineer in hydropower for a couple of years. And then after that, I moved into the district office as the chief of the mechanical design section. So supervising and overseeing about, 19 mechanical engineers, a couple of engineering technicians, and in that group was a bunch of engineers in training. So, you new graduates out of school looking to get into the engineering field, and just a lot of fun seeing those folks learn what it's like to be an engineer and develop in the field. And then about a year and a couple of months ago, 4 months ago now, I got into my current role. So I'm in operations division now. Yeah, a year and some months. This is in November, I think. So my current role is the Chief of Operations and Maintenance Technical Support. And really what I'm here to do is function in the district building to support our remote operating sites, folks like Bridget and their role as the engineering leads for the operating site, to make sure that the district is focusing on initiatives that help them get their jobs done at the field. So that's where the magic happens, is out in the field. And we're here to help ensure that they can meet their mission. So that's a little bit about who I am. Overall, been with the Corps almost 13 years now, and really, really happy to be supporting in my current role. So one of the neat things that I've been able to do was, you always ask, what's it like to be an engineer? What's it like to work for the Corps of Engineers? And what cool stuff do you get to do? Well, from time to time, some of the cool stuff you get to do isn't really dictated by management or provided in a job description or a position description. It happens as a necessity, sort of a necessity by need. So when we first started the pandemic, Bridget and I were both working full time. We had our kids at home. Daycare was closed. And we were trying to figure out how to make everything a little bit easier in life. And one of those things was how to get our design teams out into the field when they couldn't go there in person. There were a lot of restrictions for health reasons. A lot of folks were making personal choices to stay home, and otherwise we were playing safe, keeping everybody apart. And that made it very difficult for us to do business the way we normally did, which is that the engineers and scientists and technicians go out to the site, they see what they're about to do a design for, and they can do it better once they see that. So while we were trying to figure this out, we were also trying to help Bridget's mom and dad move up to the Pacific Northwest, and we were scrolling on our phones looking for houses for them to buy. And Bridget said, hey, why don't we just do this for our operating sites? And I said, I guess that's not a bad idea after I thought about it some. So we developed this system to where one person can go out to the field. They can take a couple of photos with a 360-degree panoramic camera, and we can compile it into a virtual tour. So that's really made our design team's jobs easier, facilitated making sure we can get those designs done. And that's the system that we're going to use today to show you one of our remote operating sites, which is Lookout Point Dam. So with that, I'm going to turn it back to Bridget. I'm going to let her walk you through the site virtually, and then you can see a little bit about our facility from the outside, and then I'll take you on a tour of the inside the power generating plant.
All right, thanks, Brian. So like I said, this is Lookout Point Dam, and right here we are on the roadway at the top of the dam looking downstream. The wall in the middle that you see right here separates the stilling basin, which is on the left, and the tail race, which is on the right. The stilling basin is where the spillway gates and the regulating outlets, or ROs, deposit water, and the water that flows through the turbines is released into the tail race. The building that you see down there, that is the powerhouse, which Brian will talk about, we'll walk you through next. Okay, so I'm just going to turn over here. So a little bit of dam geometry. So looking from the upstream or reservoir side of the dam, we see that Lookout Point has 5 spillway gates at the top, and it has 4 of those regulating outlets at the bottom. Passing water through the spillway and ROs does not generate power, and but to the right you see there are 3 penstocks that take water to the 3 turbines where power is generated. The turbines are each rated for 40 megawatts of power. And as far as water passage goes, under normal operations, we can pass up to 12,000 cubic feet per second. And since we're in the middle of the Olympics, just to let you know the scale of that, that would fill an Olympic-sized swimming pool in 7.33 seconds. We do have the ability to pass much more water, but we're limited by the capacity of the downstream. So if we start letting more water through the dam, we would potentially flood downstream communities. And so we're limited to that 12,000 cubic foot per second. Okay. Here are 2 cross sections through the dam. So the top shows the spillway gates at the top right here. They're radial spillway gates, and the RO gates at the bottom, RO passageways at the bottom. And then the bottom cross section shows you that passage through the penstocks to the turbines in the powerhouse. So we're gonna hop on over and go see the reservoir side here. We're gonna jump up on this traveling crane. This crane is used to put in, I don't know if it's the bulkheads or the actual RO gates, but it allows us to block off water passage to the RO gates so that we can do inspections. Okay, so this was a picture. This was a much better site visit than the gray, gloomy day that you saw before. So here we're on top of the traveling crane. This photo was taken during a relatively high pool, so the water elevation was high. In the winter months, we tend to draw down the reservoir to have more available storage during the wet season. You can see the orange boom that spans the reservoir. It's a pretty simple contraption, but it's pretty important. So the purpose of the boom is to reduce the amount of floating debris that goes through the RO tunnels over the spillway or gets matted against the penstock trash racks. And to the right over here, you can kind of see how it guides debris to the bank. And then periodically, our maintenance crews will clear that debris so that we don't damage the ROs or the turbines. Okay, we're going to go ahead and move on to some spillway machinery. Okay. So right here we see the hoist system that lifts the spillway gates. The system uses a set of one small gear, the pinion gear, that is rotated using the relatively small motor. And the small gear rotates a larger gear and uses mechanical advantage, allowing the motor and electrical components to be much smaller and cost effective. So the pinion gear is rotated by the motor, and it rotates the bowl gear, which is what the wire ropes are connected to and lift the spillway gate. So back in 2014, we did a gate and machinery rehab. So the machinery was completely replaced and the gates were modified structurally with the addition of the red stiffeners you see in this photo, stiffening the gate arms and the skin plate. Ongoing modifications that we're still working on include adding these covers to protect both the equipment and operators from the elements. And that's kind of a slow and steady progress as we move down the spillway gates, adding those. You can see we've only got one of them right now. So that's kind of an overview of the spillway and the top of the dam. And I will pass it on to Brian, who's going to, let's see.
Yeah, they're hidden back there.
Take you through the powerhouse.
All right, thanks, Bridget. And while we're talking about the system, I kind of wanted to go grab one of the cameras that we use to take these shots, just to show you. They're kind of cool. Really, really small. Definitely, fit in the palm of your hand. So this is super simple stuff, but just wanted to give you a visual for the tool that we were using as we create these tours. And with that, I'm going to take over here and I'm going to walk you through the powerhouse portion. So talk a little bit about what you see inside and what makes electricity. So first we're going to enter the big front door here. And we're going to step into the powerhouse. One thing to notice, you'll see right here on the wall, all of our sites, our project offices and our district office have big emphasis on safety of staff. So what you're looking at here is a fire escape plan, exit routes, making sure everybody knows how to get to safety. One of the first things you learn when you visit a powerhouse for the first time is you really ought to bring a flashlight with you because ironic as it may seem, the power could go out on you. And that's for any variety of reasons, but we have emergency communications, radios. Some powerhouses across the nation still have pager beeper systems, so those are kind of fun. But we make sure each of our cabinets, major equipment cabinets, also have the phone number for the control room because the control room is the accountable party for any emergencies. So safety is always a priority at the Corps of Engineers. So we're going to walk in a little bit further and show you what the generating floor looks like here. So this big yellow barrel in front of you, very large, is one of our generating units. And right at the top, you can see the number 3. Oops. You can zoom in a little bit and see it. And that's an indicator. All of our generating units have indication on top. That dome will light up when the generator is online and functioning. And that's another safety indicator. Let you know that the electricity is hot and you don't want to be working around things when they're not safe. So it lets you know what's running and when and which unit you have operating at the time. So I'm going to step over here a little bit and just give you an example of, this is kind of minor, but everything we do at our powerhouses requires operations and maintenance. And the maintenance side of things is making sure that all of the equipment that you use, wire ropes, slings, harnesses, attachment points, and other tools are taken care of. We maintain our tools. We make sure they're clean and ready to use when the need should arise. So this is a good example of some rigging and harnesses that are stored nicely and safely. So I'm going to rotate you around a little bit, and I'm going to show you what doesn't look like it, but might be the most exciting part of the tour today, and that's my terrible attempt at a pun. This piece of equipment is called the exciter, and the exciter is a critical piece of generating electricity. It's what allows us to monitor and regulate voltage as the generating unit is, the dad jokes have to come out to play, Michelle, thanks. So this unit here is what regulates voltage and allows the generating unit to stay what we call synchronized to the grid. So I won't get too in the weeds on that, but whenever we run a generator, and if that generator is going to be connected to the power grid, it needs to be synchronized so that it's not trying to what we call buck the system or run out of sync. You can cause grid instability with that and other things that we don't want to cause. So, healthy exciter, and you've got good electricity running through your unit. Taking one step down, we're going to look at another really important piece of machinery here. And this is called our governor. The governor is, it changes meanings depending on whether or not you're synchronized, so it's kind of funny. But essentially what the governor does, it's a system of pressurized hydraulic oil and valves, and it will push that oil to our wicket gate system. And the wicket gates are what open and close and allow more or less water to flow through the unit. So before the generator is synchronized to the grid, you're essentially using the governor to control the speed of the unit. The more water you have, the faster it's going to spin. Once you synchronize the unit to the grid, it can't change the speed anymore because you've synchronized. It has to run at a specific speed. So what you're really controlling is the power output coming through the generator into the transmission lines. So one of our major projects over the past, say, decade, 15 years, something like that, is we've been retrofitting these really cool old mechanical governors. They're full of pulleys and linkages, and I'll show you a picture in a second. And we've been converting them to digital. So we're using programmable logic controllers to electronically control and monitor what the governor is doing. So I'm going to click on a couple of interior pictures. This is actually the face of the cabinet. So on the left picture, on the right side of the cabinet, you'll see an example of all of the gauges that used to exist. And on the right side is a retrofitted unit, and that shows what the new, nice, handy touch screen, a lot more what we're used to in today's age, that represents all of the same information here, but on a touch panel. And if you look inside the cabinet, you'll see some of the differences. On the left side, any amount of Facebook scrolling and you'll run across something like a Rube Goldberg device. It just kind of has all kinds of linkages and pulleys for no apparent reason. Well, these all have very specific reasons, and it's really, really neat stuff to see how this was counterweighted and balanced to make the unit function smoothly and efficiently. Over time, as we've started to upgrade them, we've been able to remove some of those mechanical functions and turn them into digital controllers. So these are little hydraulic, high-pressure lines that are running to a digitally controlled proportional valve that pushes oil back and forth. And this is a feedback mechanism that tells us exactly where the hydraulic valves are located in that chamber. And that's how we know what the governor is doing and how we control it to say, go more open or more closed. And as I've said before, safety is a priority. So one feature that these have in our upgrades are if we ever lose control power or something else goes wrong, if some of our sensors aren't aligned and we don't have full visibility of what's going on with the unit, they will force a spring-operated solenoid to close and force the hydraulic oil to make the wicket gates go closed. And that shuts down our unit safely and makes sure that nobody gets hurt. So I'm going to show you one quick peek. I'm going to fly up on top of this generator barrel, and I'm going to look up here. Kind of one of the unsung heroes of the Powerhouse is the overhead bridge crane. 200 ton. Okay, yeah. So this is a 220-ton bridge crane. They can lift a massive amount of weight, and they are here when we need them to lift the large major components within the Powerhouse. And one thing that they have the capacity to do is to pick the largest and heaviest object in the power generating train. And I'll show you a cross-section of this in a minute so you can kind of get a sense of scale. But the heaviest piece on these generators is going to be the generators themselves. You got to pick them all the way out of the barrel and be able to fly them across the powerhouse and set them down into a maintenance area. And to do that, we use these really large lifting devices that you can see on the floor. Those are just standing by, waiting to be used for when we need them. So I just wanted to give you an order of magnitude for scale. I did fail to mention that these generators are, there's 3 of them at this particular powerhouse, and they generate about 146 megawatts each at full production. Oh, nope, 140, 146. 40 each. I'm being coached by the smarter engineering boss next to me. So they're 40 each. My mistake. I read a typo on my notes there. So 40 megawatts each. That does sound more right. And I'm pretty sure I saw Mr. Miles join the room, so he'll give me some correction language for that later. Steve, thanks for joining. We're going to take a quick step down. What I'd like to do next is walk you down to the lower level. I'm going to show you what happens underneath all the generating floor and governor front-end equipment. And this is what it comes down to. So I showed you the inside of the governor, and I showed you the really small hydraulic oil lines. Well, these are the big mamma jammas that come down through the floor and into a large reservoir with motor and pump system. And those are what pressurize the oil and allow it to be pumped through very large hydraulic cylinders called servo motors. And I'm going to show you those in a second. And those are what basically drive the wicket gate bull ring. Thanks, Steve. So those are what drive the bull ring that move the wicket gates open and closed. And you'll get to see how big those are in a second. So remember, you're taking a very, very tiny set of valves that can fit in my hand here, and you're using kind of similar to the gear analogy that Bridget mentioned a minute ago. It's not mechanical advantage, but in this case, it's called hydraulic and proportional advantage. You're taking a very small valve to move a little bit of oil to make a bigger spool move, and then port a much larger volume of oil through these big pipes here. I think these pipes are probably either 8 or 10-inch in diameter to give you a sense of how much oil we're pushing. And just as a neat feature of what we can do with our virtual tour system, since you can't get around and walk up close to the machinery, we can take some nice close-up photos for you, show you what those nameplates look like. And then I think what I want to do is I want to show you, I'm going to take you over a little view window here and show you what it looks like to look down at the turbine. But first, I want to highlight, again, we talk about maintaining our tools. Our tools are what enable us to keep this large, very expensive rotating machinery healthy. And I wanted you to see how big some of these tools are. I think one of the favorite tasks that the mechanic crews give to their interns when they show up on site is say, hey, go get me that wrench off the wall. And there's no way a single person could pick up one of these by themselves. So they watch them struggle for a bit and then say, okay, just kidding, that's not safe. I'm going to help you. But these are some of the coupling wrenches that are used to decouple and recouple parts of the turbine and generating shaft. It's pretty cool stuff. So if I turn around, though, I'm going to see how big that shaft is. And I'm going to take a peek over the balcony and just give you a sense of magnitude here. So if you look up, what you'll see if you went up through this floor is the generator, and that's the large rotating piece of electromechanical equipment with the poles on the outside that create the electromagnetic field. And then if you follow that shaft down, here's the coupling to the turbine shaft, which is here. And then beneath this head cover is the actual rotating blade, the turbine where the water's passing over to create energy. And these cool looking linkages here are part of what we call the bull ring that operate each individual wicket gate that allow water to increase or decrease the amount of flow over the turbine. And these cool guys back here are the servo motors I was telling you about, very large hydraulic cylinders that push this whole ring around, open or closed, open or closed. So that's the segue into the next part of our tour, where I'm going to take you inside this turbine pit a little bit And I just have a couple of shots to show you here, but I want to show you what it looks like when you're inside that area. Yeah, and I've got a, just 1 second here. Okay, so here we are. We've jumped into the turbine pit, and this is a great cross-section to show you the different pieces I was talking about. So this is where you were standing before on the generating floor when we first walked into the powerhouse. And then if you follow that shaft down, you'll end up in the turbine pit where we're standing right now. So this is the big coupling at elevation 716, it looks like, that joins the generating shaft to the turbine shaft. And then beneath that is the scroll case where the turbine spins around and produces power. In this area here is where the actual wicket gates open and close to allow more or less water to flow over the turbine. And then it shoots out the bottom and goes into the tail race. So here we are standing in front of the servo motors. Again, these linkages are huge. Very, very cool to see in person. We don't go down here when the unit is operating. They're usually barricaded off for safety. But we do have some pretty interesting safety mechanisms. So this ring right here, the bronze ring is a large screwed device that can be threaded back against the servo motor housing, and that can keep the servo motors from opening or closing. So it's another safety protection mechanism we have when we're doing maintenance or other tasks like that. I'm just going to pan around a little bit and let you see what it looks like inside the turbine pit here. And then I'll jump up here. Now what you see here, I talked about our electronic sensors earlier. These are our MLDTs here. I'll get it right. Magnetostrictive linear dynamic transducers. That's your homework for the day, if you can remember what MLDT stands for. It's basically just a rod that attaches to a control system that'll send a signal somewhere between -4 and 20 milliamps, I believe. And that electronic signal tells the computer where in space these servo motors are positioned. So we have 2 of these so that if there's ever an error with one of them, it will tell the governor, hey, something's wrong. We should probably shut down so you can figure that out. So one of the other safety and preventative measures we have on our systems. And all around, you'll see ancillary piping going to and from places. Yeah, and I don't want to focus on these just to show you that there are a lot of systems like in this area here that are cooling water, insulating oil, and other features that help us insulate, cool, and protect our turbine operating equipment. So that's the end of our turbine pit tour. And with that, what I'll do, I think, we'll kind of, I don't know how we're doing on time here, Michelle, but I think what we can do is open it up for some questions maybe in the chat, or see if anybody wants to see another specific area. We'd be happy to take you back through that and answer any questions you may have.
Oh yeah, you guys are doing great on time.
So then I'll ask, anybody at the high schools, do you want to see a specific area again? Do you have questions about how the units operate, or anything about day-to-day life when you're working at a powerhouse? Well, we always get the conversion question, and I'll see. I see that we have Steve on the line here. I think this may be in his bucket of normal talk outside of mine. Steve, do you have a sense of how many homes we would get out of 120 megawatts? How many homes of power? And it obviously, Chris, it does depend a little bit on usage and time of year and all that stuff. I'll see if I can dig up that number while we answer any other questions that come in.
But Lookout Point has 3 turbines, and each of them produce 40 megawatts. And so it's 120 megawatts for the whole facility. How is the seismic readiness? The That's a really good question. You know, some of the modifications that we made to the spillway did address some of the seismic concerns. For the most part, you know, the dam's not going to slide, but they were built in the 50s, and that was before we had a lot of the current information for seismic. But we're always making incremental improvements to make sure that we keep downstream communities safe.
I'm still looking.
Oh, and
Also looks like Owen was asking about PLCs.
Oh, okay. Could you go back over the programmable logic controllers in one of the features you showed?
I sure can. And you should know, oh yeah. Sorry, we got competing microphones going on here. I am going to show you this here, and I'll give you a little bit of my background before I explain it too deeply, just so you know my limitations. So again, I'm a mechanical engineer, and what we do with systems like this is we have a team of engineers, typically a mechanical and an electrical and a controls engineer will get together to figure out the best way to configure this system. So my area of expertise on these systems when I was at HDC was the hydraulic power system, the fluid system, and then we would interact with the electrical and the controls engineers. So I say all that because I had to learn a lot of electrical speak through osmosis. But yeah, basically what we have here is a hydraulic oil manifold with multiple ports and passageways through it that the electrically controlled, so the PLC controlled system will tell to go essentially left or right. And that was a very small hydraulic spool moving back and forth. And that would allow a small quantity of oil to go down into the larger chamber, which you see here, the big yellow area. These are big, large hydraulic spools that fill that chamber, usually on average of about 6 or 8 inches in diameter on the edges of the spool. And so the PLC controls all this. There's a, let me back out here and I'll show you again, this cabinet here, the green door, if you were to open that door, stop rotating. If you were to open this door, behind it is all of the actual logic controllers. So you got the controllers, the relays, the wiring, and then everything that connects it to the screen where the operator would control it. And so all of those control signals they're taking in information from the governor. They're going to they're going to get information like what position is the smaller spool in. They're going to get information about what position the larger servo motors are in. They're going to get information related to the speed, the actual operating speed of the unit, and information related to the electrical output at the exciter and at another place in the system to let us know how much energy is being basically sent out of the system and how much it is supposed to be sending out. And based on the feedback within that system, we can indicate any number of different types of errors that should indicate to us we need to check on something or maintain something. So again, the PLC system is both a control system and an indication system to tell us when something isn't quite going well. And while we're talking about PLCs, I'll mention something that's somewhat of a hot topic these days, and that's cybersecurity. It's important to note that these systems are essentially standalone control systems that are not accessible to the external internet. One of the things that's really important to us, not only physical safety, but cybersecurity and cyber safety. We actually have a cyber readiness month about a month ago, and they sent out fake phishing emails to all of our staff to make sure that we're thinking about the potential detriments of cyber attack and negative impacts that could occur from that. What are you thinking? Oh, yeah, and it sounds like you may be hearing more about cybersecurity later today. automated controls. So you'll be hearing from Artem in a minute here with ACCS. So that branch that you're about to hear from at 10 o'clock, Automated Controls and Cybersecurity, is a branch within the Hydroelectric Design Center that Mr. Miles, who's on the line today, is the director of. And one of the things that that branch does is help to design our hydropower controls systems. So again, these are PLC-based systems, and they help us make sure and control and monitor our generating assets to ensure that we're doing what we told the computer to do, and make sure nothing's going wrong in the process. So I'm sure you'll hear a little bit more about cybersecurity there, but it is a big part of what we have to maintain focus on here at the Corps. Any follow-ups to that, or any additional questions, other areas that we can go back and show you? Did I miss anything? Okay. Michelle, I think that's about it for us today. So we can let you take charge, either give folks a couple minutes to rest their eyeballs or do whatever else makes sense here.
Oh, sounds great. And thank you guys for doing this presentation. Like, I really, really wanted you to do it again. They did this same presentation last year at our virtual engineering week event, and it was really good. Since someone wants to be in the camera, I thought I'd share this guy. This is Scrap Iron, and he is being snuggled like a little baby. Yep. Anyway. Yeah, so up next, we have Artem talking to us. I will play a video that we have that is really cool looking, really slick, and describes more the mission of the Corps of Engineers. So I will get that ready. Once I get that kitty off my lap. And yeah, Brian, Bridget, thank you guys so much for joining us for this. There we go. Okay, so I am going to share my screen. There.
2 days after General George Washington was appointed Commander-in-Chief of the Continental Army, he asked Colonel Richard Gridley to serve the nation as the Army's first chief engineer. Our roots trace back to Colonel Gridley, and since that day, the U.S. Army Corps of Engineers has been answering the nation's call to engineer solutions for our nation's toughest challenges. When a vast new land needed to be explored and mapped, when waterways needed to be opened to allow commerce to flow, when harbor cities needed protection, the nation called on the Corps of Engineers. When the world needed to cross the Panama Canal, when NASA wanted to land on the moon, whenever our military needed something built, the nation called on us. In today's dynamic environment, our nation faces challenges both old and new, and the U.S. Army Corps of Engineers continues to answer the call.
Can you serve those in need in our communities?
When disaster strikes, we stand with our federal and state partners to restore critical public infrastructure. We have deployed thousands of experts to some of the worst natural disasters in America and around the world. Our 249th Engineer Battalion provides emergency power to help people rebuild their lives.
Can you help us reduce risk of a disaster?
Our system of dams and levees help to decrease the risk of catastrophic flooding in communities across the nation. Since 2004, these structures, along with local planning efforts, have prevented billions of dollars a year in damage.
Can you keep our waterways open for business?
Around 95% of all U.S. imports and exports, worth trillions of dollars, move on waterways and channels maintained by the Corps. We service several locks and dams which allow ships of all sizes to transit the country.
Can you help us restore the environment?
We build and restore critical wildlife habitats for endangered species, work to control invasive species, and replenish eroded shorelines and marshlands. We regulate activities that impact our nation's waterways and wetlands to protect important resources and aquatic habitats. We clean up hazardous waste, both on and off military installations.
Can you give us somewhere to enjoy nature?
As one of the nation's leading federal providers of outdoor recreation, we host about 370 million visitors to our 400 lake and river projects annually. We serve as stewards for 12 million acres of public lands and waters used for recreation, water supply, and water quality.
Can you find new solutions to tough problems?
The Corps operates multiple state-of-the-art laboratories where scientists research and develop technologies that save lives and prepare for the future. We work with our interagency partners to use our collective knowledge for the good of the nation.
Can you help us develop clean energy solutions?
The Corps of Engineers is the largest producer of hydropower in the U.S. and among the nation's leading users of clean and renewable energy. We use the latest technologies, like wind and solar, to help military installations produce as much energy on site as they use within a year.
Can you give America's military the support they deserve?
We build world-class military facilities for our service members and families to live, work, train, and heal. And we work with Veterans Affairs to make sure our vets get the kind of care they've earned. We also share our expertise with our foreign partners, deploying teams to help the people of war-torn countries rebuild their homelands and promote stability. Today, our dedicated team of military officers and Army civilians in more than 100 countries continues to answer the nation's call by always building strong.
Okay, so that was very cool advertisement video that our, I think it was put together at a headquarters level. Like, it did cover a lot of the different missions that the Corps of Engineers has. What you saw the COVID ICU buildings that we did, which was a huge effort. Another effort that we're currently doing is the Corps of Engineers is assisting the VA with their construction of the new VA building. And Portland District does not have a military mission. We're pure civil works, but some of our other districts do support military bases. Like you saw in the video, they do construction of barracks and staff housing. So there's a huge diversity of things that we do at the Corps, and we're all very, very proud to work here. So next, I'll have CJ introduce Artum, who is the Chief of the Automated Controls and Cybersecurity section.
Yeah, so it was kind of a good segue right there at the end of the Lookout Point walkthrough, because some of the questions at the end were about the PLCs that run the digital governor, and then there was a little jump off conversation about how we make sure that those digital assets are kept safe and cyber secure. And so it's a good segue into Artun Natchik, who's the Chief of the Product Support section in the Automated Controls and Cybersecurity branch. and also my supervisor. So I will only say nice things about the work he does. And I'll pass it off to Artun to take it from there.
All right. Thank you, CJ. Thank you, Michelle. Let me share my screen real quick and we can get started. All right. Hopefully everyone can see my screen. All right. Thanks, Michelle. All right. Good morning, everyone. My name is Artun Knetuk. I am a supervisory electrical engineer. I work in the product support section in the automated controls and cybersecurity branch. And kind of a big picture of what we do. A lot of it is industrial control systems, automation, and cybersecurity. So inside of the branch, we're really concerned about how can we automate some of our hydropower facilities. Let me see if I can get my laser pointer out. So I just wanted to go over a couple of these pictures you see. So this is me right here. This was me maybe 4 or 5 years ago. We were on site commissioning at a dam. We were doing some automation for one of the dams at Richard B. Russell for hydropower generation. And we didn't really have any, it was a really busy day out there. There weren't really a whole lot of desks. So we made a makeshift desk with some boxes and we got the job done. Took a while. I was TDY, or I was out there for maybe about 3 weeks. It was a ton of fun. I absolutely enjoy going on site. In this picture over here, these are two of my coworkers. They were working at Bonneville Dam. They were doing some commissioning for some of the automation on the hydropower units. So working on some PLC logic, doing some configuration on kind of the inputs and outputs, and kind of just on the industrial control system. And then this picture up here, I actually took this last week. We had a visit from the United States Bureau of Reclamation. They wanted to do some knowledge sharing on industrial control systems, automation, and cybersecurity. So we thought it'd be a great time to do some sharing of knowledge with another federal organization. So yeah, kind of the outline. What are we going to cover today? So kind of want to go over who am I? What do I do on a daily basis? What does it mean to work in industrial control systems, in automation and cybersecurity? Kind of go over what does my team do? What are they doing on a daily basis? And then kind of start jumping into, well, what are industrial control systems? It's kind of a very vague, big term. What does that mean? And then the next kind of topic I want to cover is, well, how does that apply to hydropower? How do industrial control systems apply to hydropower? And what else? What else is there about industrial control systems that we can cover? And then talk a little bit about cybersecurity. Kind of give it's a huge field, cybersecurity. Just want to go over maybe some of the highlights of cybersecurity, and then go over how do I get into industrial control systems? So how did I get started in industrial control systems? And hopefully by the end of this, you'll be interested too. So you'll have some ideas how you can get started in the industrial control systems world. And I would say my 3 key takeaways from kind of being an engineer and being in industrial control systems. And yeah, at any time, feel free to post a question about me, my background, engineering, industrial control systems, automation, and cybersecurity. Don't be shy. I would say if there's any questions, please post them in the chat. I love answering questions. And just on this slide, a couple of different pictures. This is a little bit more of what I do now as a supervisor. I'm going to call it like requirements engineering. So we want to make sure that the system we're delivering and installing on site is built correctly, kind of meeting the customer's requirements. And then down here at the bottom, this is, I'm going to say like a basic control system, maybe a very vague way of saying like, how does a control system work? And I thought it was kind of a neat picture. I kind of just put it together, and it's just going over how does data flow through an industrial control system, and maybe how does a PLC do controls on an actual actuator out in the field. So yeah, who am I? How did I get into this role? So, I'll kind of start back probably in my junior year in high school. I didn't really know what I was going to do, and I wasn't really sure whether I was going to go into college, whether I was going to get a blue collar job, or kind of like what was I going to do after high school. So around junior year, we had a similar event. It was kind of engineering day as well. And I was able to speak to a couple of different computer engineers, electrical engineers from different industries. And I think we also had a couple of college students come by, and I was kind of just asked them, what did they think about engineering? How did they get into it? Why did it spark their interest? And after talking with them, a big thing that I thought was really interesting was this idea of using math to actually solve real world problems. I was very skeptical of this idea. I can actually use algebra and trigonometry, calculus, pre-calculus to solve real world problems. And it didn't really start clicking until I went into college and said, I'm going to become a computer engineer. And I decided to go down this road, and probably my sophomore, junior year in college, I was like, wow, this is actually how I can solve problems as an engineer. And I graduated, got my degree in computer engineering. I'm originally from Knoxville, Tennessee, so I went to the University of Tennessee, got my computer engineering degree. I applied to a job at the Hydroelectric Design Center, and they flew me out for about 2 days. I did some interviews. I was able to tour around the Portland area, and they extended a job offer to me, and I took it, and I've been here ever since. So I started in 2013. I've been here since today. So coming on strong for about 9 years now, and I've loved every day of it. Probably one of the best jobs I've ever had. Absolutely love working for HDC, working for the U.S. Army Corps of Engineers. And for me, I was always kind of curious, well, what does it mean to be an engineer? What do I do? And some of my experiences as working engineer in HDC, what do I like about it and what have I seen? Some of the things are that I get to work with a fantastic team of engineers to solve complex problems at hydropower plants. There's always a new problem to work on. Even though hydropower generation has been around for decades, probably like 50, 70, 100 years plus, it seems like there's always a new challenge coming in just about every single day. And the other big thing is I've worked on automation projects for HDC as well, so the Hydroelectric Design Center. I've traveled to a whole lot of different states across the United States. I've been to Oregon, Washington, Idaho, Virginia, South Carolina, Alabama, and I've worked on all these different industrial control systems at these hydro plants. And, what are some of the other things that I really like working about for USACE? It's definitely the travel. I enjoy traveling, talking to people, seeing how the other sites do their operations. But for me, the absolute best part is whenever you get your design kind of on paper and then you actually develop it and do the programming, you go on site to do the installation, and there's no better feeling than seeing something that you have been working on for 6 months to a year actually controlling something out in the real world. It's mind-blowing. It still blows my mind every time, and I've been in this job for 9 years. And whenever it works really well, it's really cool to see. And, the other thing too is in the Army Corps, I love working with the people here. Everyone here is really passionate about hydropower, about the mission of the Army Corps. And it's great to have a team of people who are all engaged and interested in hydropower. I can always go back to the team and we can talk about how we're going to solve this problem, or what's the next upcoming thing, or talk about industry trends as well. And there's always this team to talk back to, and just a really great group of professionals to work with. So I kind of just wanted to show what are some of the different hydro dams across the United States. This is some of them. There's more. I picked just a couple of them. But here on this map, there's a huge amount of hydropower in the Northwest region. There's a smattering kind of in the central part of America. And then the second largest area is down here in the Southeast. So I kind of just wanted to go over what are some of the different dams I went to. I took a couple pictures, and yeah, just kind of talk about some of the different dams. So we'll start our journey down in the Southeast region, right around Georgia, South Carolina area. So this dam is called Hartwell Dam. This is a picture I took of it. I was out here, probably about 5 years ago. I think this picture is about 5 or 6 years old now. But this dam, it sits on the Savannah River. It's located in Anderson County, South Carolina. It has 5 generating units, and the capacity of this plant is about 420 megawatts. So between 5 units, I think about 2 of them are rated for about 90, and then the rest make up the additional megawatts for the 420 megawatt capacity. And a fun fact about this dam, I have never seen a dam with generating units that sit outside. Typically, the generating units, these big cylinders, they're sitting inside of the powerhouse, so they would sit inside like this concrete structure. And this is one of the few dams I've been to that actually has their generating units sit outside. It was pretty cool to see them dismantling one of the units when I was out there, to see it being done all kind of outside. And then next, we'll go a little bit further down the Savannah River. So Hartwell was right up here, number 65. And then as we go more southeast towards the river, we hit Thurman Dam. So Thurman Dam, it's located nearby Augusta, Georgia. It also sits on the Savannah River, so right in between Georgia and South Carolina. This project has 7 generating units, has about 380 megawatts of capacity. And with this dam, Richard B. Russell and Hartwell, they create over 120 miles of lakes that are used for recreation. So not only do they generate hydropower, but they also have a recreation aspect that they support as well. So people can go take their boats out to go fishing, go swimming, take their dogs out to go swimming. It's, when I was out here in the summertime, it was awesome to see people kind of right in front of the dam in this area fishing. And it always kind of blew my mind, like, wow, they can get so close and catch some fish. Let's see, the next dam that I've been to is right up here in the Virginia area. So still kind of in the south. And this dam was called Philpott Dam. And this is a smaller dam. It's located in Bassett, Virginia. It has 2 generating units, installed capacity of somewhere between 10 to 13 megawatts, and it sits on the Smith River. And here, this is the powerhouse, Philpott Dam. Here's the switch yard, and it's kind of sitting on an earth embankment, and then they have the large structure over here. I went with a couple of other coworkers, and when we were out there, we were looking at doing kind of like we wanted to see what sort of industrial control system they had installed, because they wanted to do an upgrade to their industrial control system. So we were talking to this guy over here. He was a mechanic, kind of let us know what the status of their industrial control system was, and he was kind of our tour guide when we were out there. And then we'll kind of visit a couple of dams up here in the northwest region. So up here, I think it's number 5. This is another dam I've been to. This is the Lower Granite Dam. And this one sits on the Snake River. It's kind of starting to grow in megawatt capacity. So this dam has about 6 generating units, about 810 megawatts of installed capacity. Sits on the Snake River. There's quite a few dams on the Snake River. And this one is located in Pomeroy, Washington. And I was out here actually just about 5 months ago doing some work at Lower Granite Dam. And on this picture, these are some transformers out here. I think if you look to the left, you'll see the forebay, and to the right is the tail race. And then if you look behind you, you would see the navigation locks. And then the last dam I'll talk about is the biggest red circle on this map. It's one of the larger hydropower plants in North America, in the United States, and that is Grand Coulee Dam. Grand Coulee Dam, it's in Electric City, Washington. They have 33 generating units, 7,000 megawatts of installed capacity. Also sits on the Columbia River. And a fun fact of Grand Coulee, they actually have 4 powerhouses, a left, a right, a third, and a pumping station. And I just kind of wanted to go over this. So just from all these different projects, we look at automating from somewhere between 10 to 12 megawatts of installed capacity, all the way up to 7,000 megawatts of installed capacity. So there's a huge, diverse range of how do we control power generation of these projects. And I wanted to go a little bit over, well, what do I do on a daily basis? What does it mean to be an engineer and a supervisor? So a couple of things that I do on the supervisory side of things. I like to think of myself as maybe wearing 2 different hats at the same time as I go through this role as being a supervisory electrical engineer. So on the supervisory side, do a lot of project management. So we have a lot of different projects going on, and we have to make sure that the financials are all in order. We're on schedule to get our project done, and the milestones are being hit. Also do a lot of mentoring. So I work a lot with new engineers, maybe some mid-career engineers as well, and do mentoring, kind of help them if they get stuck on any problems, do a lot of brainstorming with them, make sure that their skills are up to date as an engineer, and always working with them to make sure that we're kind of keeping up with the industry trends that are happening in the industrial control systems world. Hiring, a big aspect of my job is hiring. So always looking for different engineers that we can hire into our group and making sure that they have the right skills. And we're kind of doing some outreach as well to different organizations to make sure, like, hey, these are the skills that industrial control system engineers need. And the other big part of my job is contracts and acquisitions. So work with contracting, write contracts, make sure that we're buying the correct pieces and parts for industrial control systems that are being installed out at the projects. And then on the engineering side of things, a couple of different things that I do. Oh man, I do a lot of things. So probably, I'd say my favorite ones are design reviews. So as engineers, they put together designs. I do reviews on those designs. I do validation verification on them as well. So that might be doing some sort of testing on the industrial control system before we go on site to install. Might also do some testing with the customers actually coming on site, where we run through a lot of different automated tests on the industrial control system. Another big aspect of engineering is brainstorming. So a lot of collaboration, working with other engineers, working with kind of our team and making sure that is the path that we're going down the right path for the industrial control system being installed at that project. And then also the nitty gritty. So some programming, do a lot of PLC logic, a lot of PLC programming, do various programming, kind of a whole slew of different languages. Also do documentation on the engineering side. As an engineer, documentation's vitally important. Want to make sure that what we're installing is well documented so others can use the system and understand how the maintenance should be done. And then the other aspect is probably like the networking part. How do we network our system together at these hydro sites? How do they all work together? And you know, what are some things that I like about my job? So a couple of different things that I like: the mentoring, hiring, outreach, project management, financial side of things. I absolutely enjoy that. I didn't think I would as an engineer. So I was a production engineer, kind of like a programming engineer for about 5 to 6 years. And I never really thought I'd enjoy the financial side of things. But as a supervisor, that's a big part of my job. And that it's a lot more fun than I thought, doing the economic analysis of our different projects. The other big parts that I like are kind of working together as a team to solve complex problems. So there's a lot of different complex problems coming up in industrial control systems, and kind of working with the team, building the team members up to solve those problems. It's a lot of fun. It's a lot of fun to work with like-minded engineers to solve complicated and complex problems. And what do I like about working as an engineer? I enjoy solving challenging problems. So we have really complex problems that come in, I feel like almost every day, and then we have to solve them either right then and there, or we have to solve them within a week and have some sort of resolution to these problems. The other big thing I like is seeing the results of my work go out into the field. So being able to travel to some of these sites, seeing the results of my work, controlling the hydro unit, maybe controlling the spillway gate. It's absolutely fascinating. It's a great feeling too to see like all this hard work I did back in the office, working with our customers, with other engineers out in the field, and going from design development to on-site installation and being there to see it running for the first time. Fantastic feeling. I absolutely adore that as an engineer. It's not just all theoretical work, it's actually hands-on work. And a big part of kind of like, well, why do I do my job every day? What's my biggest inspiration to get my job done? And I really feel like for me, it's about delivering renewable energy to towns and cities. The work that I do has a major impact on people's lives by generating power. We generate power for the whole Northwest region with hydropower. We're a huge contributor to the electric grid. Down in the Southeast, we're also a big contributor for real power, megawatts. And yeah, there's no greater feeling than like, hey, I'm actually contributing to the electric grid and we're producing some power out here. And, you know, I would say there's a couple things I don't like about my job. It's probably that Sometimes we get some tight deadlines and some long days. So sometimes we have to buckle down, get the work done, and maybe a project needs to be completed a little bit earlier than it was originally scheduled for, or there needs to be some problem that needs to be resolved as quickly as possible. We want our industrial control system to be running as soon as possible, or the availability is always there. So there might be a couple long days sprinkled throughout the year that we just have to kind of hunker down, maybe work a 12-hour day to get some of that work completed. So what does my team do? So I'm one person. I'm a supervisor. I'm an engineer, but I also have a team that works under me, and they're the ones who do a lot of the heavy lifting. They do design, development, and implementation of industrial control systems. So they're designing industrial control systems for hydropower plants, making sure that we have our network diagrams put together, that we're meeting all the stakeholder needs. So if they want to do some automation, if they don't want to do some automation, if they want to see certain data on the screens or not, they're doing a lot of the heavy lifting. And I do some of the review work and some of the validation work. They're also doing a lot of the development. So they're programming, configuring, setting up test rigs, really getting down into the deep knowledge of like what needs to be done on the industrial control systems. And what sort of programming do they do? Oh, this can be anything from programming controllers, setting up input-output cards, scripting languages like Python, PowerShell, Perl, compiled languages like C, C++. There's a whole slew. There's a whole slew of different things that go on to do an industrial control system. And it's kind of just scratching the surface of what my team does. And I think the other thing that they also do that's really big is kind of the implementation part. They travel on site and they do the actual install on site. We have a couple different installs that'll be happening actually next week. We're planning for about 2 weeks for them to be on site. And I think a lot of people in my group, they do enjoy that aspect quite a bit. And I think the other big piece, probably in the design aspect, is making sure that our system architectures are like secure. We really want to make sure that the system architecture for the industrial control system is operating as best as it possibly can in these industrial environments, in the hydropower environments. And a couple other things kind of being like, what does my team do? And how do I work together with my team? Where we have to work together as a team. I know when I was in school, high school, college, I always dreaded doing group projects. I was like, oh no, I have to work with 5 other people and we have to get this work done. It was just, I always kind of felt a little bit like a mess. But when you're in the professional environment, this is what you do every single day, if not every single hour. You're working with other engineers, working with other customers, and you're just trying to understand how can I build a system that will work for them. And I think after about 9 years being in this industry, communication, collaboration, cooperation, working with other engineers, so vitally important. I think it's a huge skill to have as an engineer, being able to communicate with other engineers. And then the last piece that my team does, after going on site, we've installed the industrial control system. It's up and running. We've commissioned it based on the specifications of the customer. We do maintenance on the industrial control system. So make sure that it's running as best as it possibly can out in the field. So if there's any issues that come up, they'll call my team for help. They'll call other engineers for support if they want to add some features. So let's say they want to add something to a PLC, like a new run on this PLC logic. One of the engineers on my team would do that sort of work. So that's kind of what I do, what my team does, a little bit of how do we get work done. So what are industrial control systems? What are they? If you're not in the industry or in the field, it's kind of hard to know what exactly they're used for or why we even have them. So industrial control systems, they're used for industrial process control. Sounds very redundant, but things like chemical processing, power generation, which is what we're in, oil and gas processing, telecommunications, navigation locks, and just about anything else you can think of for industrial process control. Industrial control systems are used for that. And the industrial control system, it's it's a very general term. It encompasses several types of control systems. There's things called like SCADA, so supervisory control and data acquisition. There's distributed control systems. Industrial control system is the superset or the overarching term to describe all those. And on this slide, this is a very high overview of, well, what does industrial control system do? So if I'm at an industrial environment, how does it work? So one of the first things is we receive data from sensors. So down here, there might be some sensors, actuators, some data though that we have to get from some component out in the field, and we need to present it to the plant operator or to some human to actually make sense of that data. So we grab this data, it goes up to this PLC RTU, kind of in the level 1 realm. And then we present this data to the operator. So we're grabbing electrical signals, maybe like a negative 10 to 10 volt signal, maybe a 0 to 20 milliamp signal, 4 to 20 milliamp signal. And we convert that into some sort of signal that makes sense to the operator. And the operator sees it here, maybe on an HMI, human machine interface. And they start thinking to themselves, well, what do I need to do with this data? And they start comparing this data to desired set points. If I'm at a chemical processing plant, maybe the set point needs to be higher or lower to complete this chemical process. If I'm in power generation, I might need to lower or raise my megawatts to achieve what the balancing authority needs. And then the operator actually does some sort of command. So they might say, okay, actuator raise or lower, or move the wicket gates on a hydro unit, and an actual physical thing out in the real world will move. And then the operator will receive that data from the sensor again, and the process will just keep repeating over and over and over on a daily basis. And they'll kind of see like, how's the process working out in the field? And this is kind of a very vague and big description of how industrial control systems help the plant operators out in the field. And I'll just run through this diagram real quick. This is kind of, it's called the Purdue model. It's something that's used out in the industry, but they kind of call level 0 like the process. So this is sensors, actuators, field instrumentation. Level 1 is PLCs. PLCs, programmable relays, RTUs, remote terminal units. This is where the actual, I'm going to say, control theory starts taking place. So how do we actually start controlling this process out in the real world? And how do we program those devices? Level 2, this one is, how do we display data to the operators? So if I'm the operator of an oil and gas processing plant, what do I want to see on my computer screen? What do I need to see? What alarms do I need to see? That's what this would be on this level. The SCADA would be maybe some sort of supervisory control. So maybe some automation that we have to program for the operator to do some sort of control actions on their behalf. Level 3, this one is, it's a little bit higher level, and it's more so for if we want to do overarching plant controls versus just a control per device or per actuator. So there might be some historical data we want to store on the historian. There might be some sort of energy, maybe like management system, or maybe even like an overarching plant management system. And then in the DMZ level, so if you want to connect your SCADA or your ICS to some other system, there needs to be a DMZ. Basically just a fancy word to say that this is the door with a guard between an ICS and other potential networks that you want to connect to your ICS. And then at the very top, there might be the enterprise level. So this is corporate level services like email, maybe DNS, web server, maybe some other PCs that you want to connect up to your SCADA system. So I would say this is a pretty good representation of different ICS systems, SCADAs, DCSs that you might see out in the wild. And the big part about industrial control systems, and this is a big part of what we do as kind of SCADA engineers, as engineers in general, is how much automation is needed for your process or your project. In the power generation industry, it just depends on that plant and the balancing authority. At other sites, maybe they'll want some more automation, maybe they'll want some less. If they want more automation, there's gonna be more programming you have to do, more math that's gonna be involved. and just more collaboration, communication with your customers and with other engineers to understand what needs to be done. So the next slide is, well, talk about industrial control systems, kind of in a vague term. How does it apply to hydropower? How do we apply this industrial control system concept to hydropower? So the general concept, it still applies. We still receive data from sensors. We present that data to operators. The operators have to interpret that data and have some idea of like, well, what do I need to do at this point? Do I need to raise megawatts, lower amps? What should I do? The operators do some sort of commands, and then the process keeps repeating infinitely until I guess they're done for the day, off their shift, and then they get new operators on. But so we tailor this concept to hydropower. So instead of just data, we actually receive power quantities from the hydro units. This could be real power like watts. It could be imaginary power like VARs, amps, volts, and breaker position, and a whole more other indication that the operator might need to do control of their hydro units. We also receive other data from the hydro units. This could be water flow coming out of the hydro unit. This could be temperatures. Maybe there's some efficiencies that we want to grab from the hydro unit as well to say, this is how efficient the unit's operating or generating megawatts at. And a big piece of, I'm going to say, industrial control systems and hydropower is based on the grid needs. So it's not just an operator saying, well, I see that we're generating, let's just say like 50 megawatts at this plant, that's good enough. It's really dependent on what does the electric grid need? Do we need to generate more power? Do we need to generate less power? Are there more loads coming on? Are there motors coming on, coming off? And based off of that, the balancing authority will direct the project to a set point. So they'll tell the operator, we need 100 megawatts for this hour because we have this huge load coming online. We have to support it. And that's kind of where this part comes in. So whenever the balancing authority, someone like EPA or Power Marketing Administration will say, we need 100 megawatts, let's get to it. At this point, the operator will say, oh man, I need to start generating more and meet the desired set point of the balancing authority. And the units are going to be controlled to the desired set point, and power is generated by the unit, and we all get power. So as I'm sitting here at home, I get power from the electric grid from hydro units. They could be generating now, they might be generating a little bit less. And it's all based on how much automation is needed as well. So some of these processes are very operator dependent, and it's up to them to decide how much do they want the industrial control system to use the automation or not use the automation. And this picture, it's pretty similar to the last picture, but there's just a couple differences. It's more tailored towards hydropower. So we got our generating units down here. We got some protective relaying, goes up to an RTU cabinet. We have some IO tied to our RTU cabinet, goes into some sort of control network where everything's connected together. And we might be getting some of our data from a balancing authority. So someone might be saying, how does the balancing authority, what sort of megawatts do they want at this time? Or how many VARs do we need to produce? Or how do we support the voltage on the switch yard? And we also have some operator view stations. This is where the operator would actually be sitting at and viewing what's happening at the hydro plant. Right. Let's see, what else? What else is there about industrial control systems, hydropower? There's a lot. There's a whole lot more to industrial control systems. I work in one industry in hydro or in power generation, and that's just in hydropower generation. Within the power generation industry, there are other industries from solar, wind, coal, gas, nuclear, and I'm just a small sliver of the power generation industrial control system world. There's the oil and gas processing world, telecommunications, navigation locks to distribute goods across the United States. So barges passing through the rivers, passing through navlocks, all have industrial control systems. Manufacturing, physical security for buildings. These all have industrial control systems. And it's a very diverse field. The industry is always looking for ways to automate processes, maybe to drive costs down, maybe to make things a little bit easier on the operators on site. And this could be applied to food processing, pharmaceuticals, power generation. Just about anything that's an industrial environment will have some sort of industrial control systems at this point. And there's always this balance. There's a delicate balance between how much automation is needed and how much human control is needed. And it's really dependent on the industry that you're working with. So in the power generation industry that I work in, hydropower, there's more human intervention than automation. And I think the general trend is that there's going to just be more automation in the future. You have to do, some processes just want to do more with less. And another big piece of industrial control systems is cybersecurity. This is a topic all of in itself, but cybersecurity is extremely important. I think in like a sentence, cybersecurity can be kind of whittled down to it's the prevention of damage to kind of an information technology systems. And we want to make sure that availability, integrity, and confidentiality are all still working with that within that industrial control system. So a big piece of what my team does, what I do, whenever we design an industrial control system, it's about designing a trustworthy system to hit those three core tenets of cybersecurity: confidentiality, integrity, and availability. And it's kind of like what I said, cybersecurity, could probably spend a whole week just talking about cybersecurity. It's a huge field. Probably in the past decade, it's been growing exponentially. And yeah, I guess that's kind of all I can really say about cybersecurity. It's just such a big field. It's very diverse. It's just as diverse as industrial control systems. And the big thing for us in my section, the automated controls and cybersecurity branch that I work in, we want to make sure that there's no way for our ICS to get compromised. These are critical processes that are running out in these projects from these industrial environments. And if they were to get compromised, there could be some adverse effects to the electric grid, or if it's a chemical processing plant, to the environment, or if it's a wastewater facility and someone was able to cause malicious harm to that wastewater facility, they could dump all the wastewater into actual clean water. So cybersecurity is extremely important for industrial control systems. And the other big piece of it is, I would call it dependability. You want to make sure that the cybersecurity of your system is dependable, but also the underlying system is dependable as well. So if you're automating power generation, you want to make sure that it's a dependable system that's automating power generation. And the really important piece too is the industrial control system, it's there to support the mission. So the industrial control system, we want to make sure that we got our process working correctly. So if we need to generate hydropower, it's a dependable system to generate hydropower. And we can do that and have a lot of trust that it's going to do that as well. And kind of this picture on the side right here, I would say in this day and age, if you aren't aware of cybersecurity and you're in the industrial control system field, you might be in danger. It's, there might be some adverse effects to your system. It's growing fast. There's always some sort of concepts that we have to look out for to make sure that our system won't get compromised, just because some of these processes are so critical to the system. And I think overall, it's a really big growing field. The jobs are becoming more well-defined in cybersecurity, and there's things like risk management, software development, systems architecture, policy and planning, cyber operations, forensics, and much more. There's a whole nother branch of engineering just within cybersecurity. So kind of went over what is industrial controls. So how do I get into it? What are some things that are really interesting, or how did I get into industrial controls? And I think for me, some of the ways that I got into industrial controls was I got a degree in engineering. So I got a computer engineering degree. If you get a degree in mechanical, civil, electrical, electronics, you can get into industrial control systems. It's such a large and diverse field that I feel like just about any engineer who has this sort of training can get into industrial control systems. And some of my things that I've noticed that have really helped me from going through college and working in the industry is learning math skills, or learning math builds critical skills. I use math on a daily basis, and some of it is not as deep as some of these equations on the right. It could be narrowed down a little bit easier, but they're critical skills. Applying this theoretical math that you learn in college and applying it to the real world as an engineer, I do it every day. Programming skills are invaluable. Learning programming from compiled languages like C, C++, to scripting languages like Python, Perl, PowerShell. This is just a must as an engineer at this point. As you learn these programming skills, they help so much to be able to automate processes in industrial control systems. And they also help with kind of doing some spot checking and validation as well. Cybersecurity is constantly evolving. If you start thinking about cybersecurity as you work in industrial control systems, helps a lot. It's a big field. It's always going to be growing, and I don't really see it stopping to grow anytime soon. And for me, a big part of what I learned in college was critical thinking. So as I went through college to get my engineering degree, critical thinking was kind of the foundation for all of my other skills in engineering. Being able to ask deep technical questions, being able to think through problems, and having that critical thinking was just a big foundation in me becoming an engineer. And I would say I use all these skills on a daily basis. Critical thinking, about designs, implementation, commissioning. If I'm on site and we're installing an industrial control system, I have to be able to critically think through what is this going to look like once it's installed. I need to talk to the customers here. Maybe there's a requirement that wasn't fully fleshed out, and I have to work with them to make sure that that's actually implemented into the system. And yeah, I think the other thing too is cybersecurity, it's a big field. So there's engineering within cybersecurity, security systems engineering, compliance engineer. It's a growing field. Since industrial control systems are an information technology product, there's a large component of it has cybersecurity built in as well. And my 3 key takeaways. So I think engineering is a ton of fun. I enjoy it so much. I enjoy taking things from paper, going through this development phase, and then going on site and actually controlling a real machine. Something as large as a 100 megawatt unit that might weigh 40 tons is being controlled by some of the programming that I've done in the office. Industrial control systems is a diverse field. It's just about anything that's in the industry, manufacturing, distribution, chemical processing, telecommunications. If you can think of it in the industrial world, there's an industrial control system controlling it. And I'm biased, but I think computer engineering is the best engineering field. I learned software development, math skills, electrical engineering skills, electronic skills for my computer engineering degree, and it's helped me every single day as I've gone through to implement industrial control systems. And, a couple other notes too about being an engineer. I think one of the big benefits of being an engineer is the pay's pretty good. You get paid pretty well to be an engineer. So for my group, if you're just starting out, some of the salary ranges I pulled out of some tables. If you're starting out, it's about $64,000 to $95,000 as an industrial controls engineer. If you're about mid-career, it's about $95,000 to $125,000. And a senior engineer is somewhere between $115,000 to $150,000. And these jobs, they're very similar in the Portland area. So my industrial controls experience is all in the federal government, but all across Portland, Northwest Natural, Pacificor, PG&E, engineering consulting firms, the pay could be similar. It might be a little bit more. It really depends on the skill set you have, but this concept of industrial control systems is so broad. There's jobs everywhere for this sort of work. And I would also say, if you can meld in your engineering skills with some of the cybersecurity skills, huge plus in the industry. People will be clamoring to hire you in their firms to be able to help design, implement, commission industrial control systems that are designed in a trustworthy manner. And then, I think probably like the last thing for me too. It's a huge field. I think I've said this before multiple times. And there's just a lot of jobs, a lot of different jobs in the industrial control engineering world. You can work about in any industry nowadays, and there's going to be some sort of industrial control systems in that industry. So even Amazon, Google, Intel, they have industrial control engineers because they have to control the temperature of their servers and their server farms and make sure the HVAC systems are working correctly. In the food industry, they're hiring industrial control engineers to automate their potato chip making process. So there's like Frito-Lay has industrial control engineers that are programming their PLCs to automate that process. Pharmaceutical companies also are hiring process engineers, industrial control engineers to build those processes that they need to produce pharmaceuticals. And the other big thing about industrial control systems, you can really spend your whole career specializing in certain aspects in industrial control systems. So algorithms, the theory behind it, you can specialize in application, cybersecurity, and design. It's such a broad field. You could spend 30 plus years specializing in one feature of a industrial control system, or you could be broad and kind of tackle a lot of different aspects of industrial control systems like design, implementation, programming, and be more of like a master of all trades sort of engineer. But that's all I had today. I think overall, you know, I really enjoyed it. I've really enjoyed being in the industrial control systems engineering field. I've done it for 9 years. I think it's a great career choice. I love it every day. There's always something new coming in every day, always some sort of new problem that needs to be solved.
Very cool. Thank you for your presentation, Artem. Does anyone have any questions?
You know, I would say that I think one of the reasons we wanted our team to do a presentation was that our group, ACCS, is kind of an interesting group at the core. We have computer engineers and electrical engineers and one mechanical engineer and a bunch of cybersecurity professionals. And so it's a really interesting example of how you can go to engineering school and think that you know what that engineering degree will do in terms of your path, and then find out that you, by way of getting an engineering degree, have really gotten a minor in learning how to learn the critical thinking aspect that Artem was talking about, and that by just choosing any one of the engineering paths, you'll actually find that it's pretty open for what you can do with it. And Artem, I don't know if you want to kind of describe what made you choose computer engineering specifically, or whether you guessed that you would be doing industrial control systems with a computer engineering degree, or how that came about.
Yeah, absolutely. So for me, when I was a junior in high school, we had something similar to Engineering Day. And I talked to a couple of engineers from Cisco, and I think there was a couple of engineers from Eaton as well. And they were computer engineers, and they were kind of talking about their experiences. What does it mean to be a computer engineer? And I was really interested in the software development side of things, but also the hardware side of things. So I kind of wanted a blend of both worlds. And the computer engineering classes, whenever I was looking through kind of the college registration, computer engineering hit both. They both hit the hardware side of things. So how does computer architecture work? Why do we have RAM in computers and processors? But there was also the software development side of things, and that was a large part of what I was interested in as well. Was, well, how do you do programming on an enterprise level? That's really what drove me towards computer engineering.
So my question is, what's the difference between computer engineering and computer science?
Yeah, that's a great question, Michelle. I really think in computer science, you spend a lot more time maybe in some of the more abstract mathematics, and also a lot heavier in kind of the software development side of things. You don't really touch the hardware side of things. So you don't take any classes in electrical engineering or electronics engineering. And I had to take about 2 to 3 semesters worth of those classes. So really did a heavy dive in power generation, in circuit analysis, in electronics as well. So the computer engineering side was this really neat blend of both worlds.
Very cool. So if no one has any more questions, I would love questions though, if you do have them. I have posted the event feedback form in the chat. We do have gift cards or USACE merchandise that we plan on raffling off. There is a space to put your email in the evaluation form, and we would love to have your feedback. I wanted to thank our team for coming here and presenting ACCS to us. I'm a dirt person. I'm a geologist, so I actually know absolutely nothing about this field, and it was really cool to learn about.
Yeah, thanks for having me, Michelle. It was a lot of fun talking about industrial control systems, how I got into it, and some of my background.
Thank you. Yeah, and Colonel Wiley, if you don't mind, if you could give the feedback form to the other students who were in the earlier sessions, we would love to hear from them what they thought of the different presentations. Oh, thank you, sir. Okay, so thank you guys all for joining us today. I have not shared my screen yet. I'll do that real quick. Okay, so today we had a really wonderful introduction to the Corps of Engineers and the different aspects we color. Tomorrow, tomorrow we have presentations on different types of engineering, and I'm looking forward to that. We will be going through hydraulic engineering, geotechnical engineering. We got the mechanical to cover this session, structural engineering, and also electrical engineering. So it should be a really exciting introduction to the plethora of different engineering types that we serve as a course. Okay. So I hope that if you guys are available, you're able to come to that event also. And thank you guys for joining us today. It was great. Okay. So with that, I think we can go ahead and probably conclude the event, but thank you guys so much for being here. Oh, yes, sir, I can do that.